here. Yeah, so today our topic is lift. How does the wind actually work with our sails to make our boat move? So some of you may or may not have got the story of all the whole Bernoulli's Principle thing and all that. So let me pull up, let me screen share my notes. That'll probably be the easiest way to do this. Pull up this guy. Boom. There we go. Yeah, so if anybody has not heard the that story, that typically goes down, usually something what you see is, if that's visible, usually you see something like this. People say, well, look, sailing works like an airplane wing. So we have our wing like this, right? And we have air coming to the wing. And this air, some of it goes over the top and some goes underneath. This is also a weird angle, but it looks like we can see things. I think we're good. So some of this air goes over the top of the wing. Some of it goes over the bottom of the wing. And this air that's split, it has to come back at the end of the wing and join up together in exactly the same spot it left. So in order to do that, the air on the top has to go faster than the air on the bottom. And there's this dude whose last name was Bernoulli, because I assume he was Italian, and he did science.
Italian.
Yes, he did science. So he had a theory, a principle named after him. So it's the Bernoulli Principle, and it says that if something is moving faster, in a rough paraphrase, the pressure over there is going to decrease. So this air that's moving faster than this air causes lower pressure on this side of things. And that makes the wing move up into the lower pressure. The wing is kind of getting sucked up into that lower pressure. And because the wing is attached to the airplane, that makes the airplane move up as well. And it kind of makes sense in your head. But then if you start thinking about it a little more and start asking a couple different questions, it doesn't quite work as well, right? So if we ask, one question that might not quite make sense is like, why do these air particles have to perfectly match up at the end? Maybe, I don't know, maybe there's some scientific reason, so I'll let that one go. But what about if an airplane's flying upside down? If it's only the curved part that makes that low pressure, right? Then what happens when you have, one of those stunt planes that comes down the airstrip at the air show, and it's going upside down, and it's like 20 feet off the ground or wherever it is, right? But now the wing, because it's upside down, now the wing looks like this. So are we saying that the low pressure should be here and we're sucking the plane down to the ground? But that doesn't really work because that's not what happens. Or what about if we switch from looking at an airplane wing and we say now we are looking at sails. If we draw a picture of our sail, it doesn't look like this, right? It doesn't look like that. It looks like this. It's not a 3D object. It's basically just a flat sheet. And so going on this side versus going on this side isn't really any difference in distance, right? Going on the inside of the sail versus going on the outside, there's no difference in how far you have to travel. It's the same. Because the air is not going to go straight here, because that means that suddenly right in the middle here, there's nothing. So it's not gonna, that's not gonna happen, because that'd be a vacuum. We can't just create a vacuum. That doesn't happen in nature. So it doesn't really happen that way. So that explanation kind of doesn't really make sense anymore, right? Or what about when you make a paper airplane? You don't put any weird sort of curve in that wing, and it's still able to kind of fly through the air. So that doesn't work. It's a cool story, but that's actually not what's happening. So it turns out that we can actually create lift even if we just have a flat board. And so, whoops, scroll down a little too far there. So when we're kind of going through the basic explanation, we'll just use a flat board because, you know, that's a little simpler than trying to deal with curves in our sail and that sort of thing. So we'll start out, and we're going to pretend for a second, just to get the idea of what's going on, that we don't have any friction, right? Just like when we have those little math problems that are like, how far would your car roll? And you just take friction out because we haven't dealt with that just yet. So we'll start simple and get a little more complicated as we go. So basically, we have our we've got our flat plate, because we said we're not using a sail yet, not introducing that extra bit of curve. We just got a flat board. If there were no friction, then we've got the air coming in. There we go, normal arrow. We've got air coming in, it goes around, and we have this thing, it's called a stagnation streamline. And that's, you know, we don't have to remember the science terms, it's just how this guy is describing it. But basically, you can think of it like this is the continental divide of where the air goes. So any of the air that's above this arrow is going to go over the top of the board, and any of the air that's below this arrow is going to go below the board. It just happens to be where that cut is. So it's not going to, I forgot what I was going to say. So we've got this, right? We've got this continental divide. Some air goes over the top, and it kind of flows around. It does kind of stick to this board, right? It flows around the board, but then it keeps going in the same direction that it started from. Same here. If it's going underneath, it's flowing around the board, and it keeps going. Now, if we scroll down a little bit, if I can do that, there we go. Turns out that if we look real close at the bottom of the whole board there, when the air is coming over the top, remember this is all the air that went over the top of the board, it doesn't come all the way right to the tip of this board. So it's based on where it started from. It's not just coming from the very tip of the board back up here. It's kind of going up a little bit and then coming over. We kind of saw that in the last picture. But because of that, if it didn't start right from the tip up here, so it can't come right to the tip down here, or it would kind of be creating a void, a vacuum somewhere else, right? We can only have as much air as we have. That didn't make sense. The air coming down, it started from over here, right? We've got the air kind of cuts here, so it can't, confusing what I'm trying to say here. I'm sorry. Let me back up so I can explain this a little more easily. So air is coming to this board. Part of it goes around the top, part goes underneath. All right. So remember that air, it's not little streams all coming down together, right? It's just one big mass. So if we split things in half, we've got to come back and close that split later on, right? We can't leave the split. We can't leave an open pocket, because an open pocket would be a vacuum, and we can't get a vacuum in nature. So that's always going to come back and close. So that's why this air is coming off the back of the board before the actual end, right? Because if it went all the way to the end, we'd be leaving a pocket somewhere over here. So it's got to come back and close itself up. Because it's doing that, there is a little space where that stagnation streamline, that continental divide, that this air on top has left the board. There's still a little space here. So again, we've got to fill the space because we can't have a vacuum, right? So this air coming down, it's actually going to turn around a little bit and close up that vacuum, and then it's going to keep going in the same direction. All right, so that's what's going on when the air comes down and hits this board. Remember, this is with no friction, so this isn't actually what's happening. This is just give us a baseline, tell us what these couple words are, what's trying to go on. But we do live in a world with friction, or viscosity, as we call it. Remember, that was something we talked about last week when we were, I think it was last week, one of those days when we were talking about how the light air works in the water. Remember, there's the air right down at the water. It sticks to the water. It doesn't move. And then there's that boundary layer. The farther you get away from the water, the faster the air is able to move. But there is kind of that gradation, that going from zero velocity, a little faster, a little faster, a little faster as you get further away, up to some final point where it is going its full speed again. Remember, we called that the boundary layer. So just like air over top of the water, we also have a boundary layer for air coming onto the sail. So just like we described with the water, that air that's hitting the sail or hitting our plate right now that we're talking about, the air right at the surface is not going to be moving. It's going to be stopped right on that plate. Then we still have this boundary layer, right down here. It's stopped. It goes a little faster, a little faster, a little faster as it starts getting away till we get to the edge of the boundary layer, and above that boundary layer, the air is going to go the same speed again. The thing about the boundary layer, though, a couple things that weren't really relevant in when we were talking through our light air, our wind situation, but are a little more relevant for us right now, is that the boundary layer does not like to have to suddenly slow down or suddenly make real sharp turns, right? So when we've talked before about the idea of your airflow might separate from your sail, and we don't like that. But this is why it might separate from the sail. If we don't have our sails trimmed the right way, then if our boundary layer has to suddenly make a sharp turn, then it might come off the back. And so here's an image. This is in water because it's kind of easier to see that than in air, but all fluids are going to behave the same, whether they're air or water or something else. So you've got kind of this mock-up of a sail there, and we can see this is separation. The water flow has separated from the back side of the sail, and so we get all these little swirls, all this turbulence, and so that is not creating lift for us. So that's not what we want to happen. So we have to make sure that our sails are trimmed correctly so that the boundary layer doesn't have to make that sudden sharp turn. Right? It doesn't want to make that sudden sharp turn or be suddenly slowed down. Now, because of when we talked just a minute earlier about the air is going to flow along the back of the plate, and then it's going to leave. It can't go all the way to the tip. So we have this little spot here on the lower side of that continental divide where the air needs to come back into, right? But because we have viscosity, we have friction, we have that boundary layer, the boundary layer does not like to take a sudden sharp turn. So when it tries to turn back here, it's going to separate from the tip of the sail, not from the whole backside, but just from right here. This portion of air that's been coming down the lower side, or the inside of our sail if we're thinking of it that way, but we'll just keep calling it the lower side or the upper side to not confuse ourselves. We've got this air coming around the lower side. It's trying to go back in there to fill that little void, but it can't. It rips itself off. It starts kind of spinning right here. Little kind of pinwheel in the air, right? So it's come off the sail, and then it kind of leaves from there. But it still hasn't been able to fill that void, right? That open space that needs to have something in it. This air from the lower side wasn't able to go back in there. It ripped off. So what has to happen then is that air from the upper side has got to be pulled down into that little vacuum. And so we're going to, because we need air to come into that vacuum, remember we said there's not enough on the upper side to actually go there. That's why it left in the first place. That's why the air from the lower side had to come back and fill that. If the air from the lower side can't do it, air from the upper side has to do it, which means we have to go and send more air over the upper side. If the air from the lower side can't do it and the air from the upper side can't do it, we've just got to come up with more air. So some air that would have gone over down under the lower side is now actually going to shift and go over the upper side of the plate of our sail, right? So that's what's going to come down around the back side of our sail, the upper side of our plate, however we're saying it, and that's going to fill in that spot. So now, because it's doing that, there's no need for that air from the lower side to try to curl over. There's no void anymore because the air from the upper side is filling it. So now this air is able to come straight off the sail. This air is able to come straight off the sail. There's no need to turn anymore. It's getting, this air from the upper side is getting sucked into this spot. And so it's not going to rip off this back of the sail and keep going. It's going to keep going in the same direction as the plate. Same here. There's no reason that this air on the lower side is trying to move up into this little spot, because there is no spot anymore. So it also keeps going straight. So now these two halves of air are coming back together, and they don't really care if they meet exactly where they left, right? That's maybe the big difference we might say from that old Bernoulli explanation, right? It doesn't matter where it comes back. The point is they're coming back together, they're meeting again, and they're going, if we look at this, they're going this direction where the plate is pointing. They're not going the direction they used to be going. So that's the key factor here. That's what's actually working for us. This little thing, apparently there's some dude named Kutta, that last name obviously, but apparently he was the one who came up with this, just like Bernoulli came up with the Bernoulli Principle. So I don't know what nationality Kutta was, maybe Indian, I don't know, total guess. At any rate, that's what's going on here. So if we look next up, the only thing we really need to explain this is that we have Newton's third law, right? So equal and opposite reaction. If we throw something one direction, there's an equal and opposite force pushing the opposite direction. It's how the rockets work, right? They throw something out the back real fast and makes the rocket go up or forward, whatever direction it's pointing. But because we took air that was going left to right on our screen, and now it's going kind of diagonally down left to right, that's been a change. There's been some force enacted on it, right? So all this kind of plays into it, whether it's this air that's being deflected here, it's this air that's being pulled into this vacuum, but that all adds up to cause a net change in the direction. If there is a change in direction, there was some force put into it. If there was a force put into it, there's a force going the other way. So this air that's been deflected this direction, that's a net force, was moving it from up to down. So that means on our board, there's a net force from down to up, right? So that's where we're getting that lift going on. So if we look at what sort of forces we do have there, there's actually two different things acting on our sail, right? So because we live in a world with friction, we've actually got two forces. We have lift, which is what we just described. Since the air has been forced from up to down, our sail is forced from down to up. That's the lift. But we also have friction. We have that boundary layer that is kind of scraping along the back of the sail here, right? So we have something called drag. It's basically the friction force. It's going to act in the same direction as the wind, as the air. So we've got air going from left to right. That means drag is also going to go left to right. So if we drew that up, it'd be one arrow going straight up on our diagram, on our page here. That's our lift. And then we'd have one arrow going from left to right. That would be our drag, right? So whenever we are doing any sort of setup with our sails and we're changing the shape and causing more power to be put in, or maybe less power if we're flattening it, whatever the case may be, we're always trying to find the best combination that we can of more lift and less drag. So there's always going to be drag, there's always going to be lift, but we have to find what gives us the least amount of drag for the relative most amount of lift. So if you just threw in random numbers, maybe you can get 20 pounds of lift and 20 pounds of drag, but we could also make a different setting on our sail and get 18 pounds of lift and 10 pounds of drag. Well, I'll take a little less lift if it gives me a lot less drag, right? So that sort of thing. We're not going to talk specifically about how to set up sales today, but that's that's the main idea. We've said that many times before. And then circulation. This was something that I wasn't, I'm not sure if I've quite got the idea down, but I'll see what I can do. I'll see if I can explain this. It turns out there's not just this stuff, but also there's another little component going on. So if we remember back up here, we had this thing we called the starting vortex, this little thing that this air is trying to come around the back, and it rips off and it makes a little pinwheel, little hurricane, teeny tiny hurricane in the air. And then that goes away once we get this flow started up, right? We get the air coming around the top of the plate is sucked into this void. So there's no need for the air to come back, from the air from the lower side to come back into this little void. But we did at some point have that little thing starting up. And anytime something changes, right, as long as the air stays the same and our sail stays the same, then this will all stay consistent. We'll have that kata condition going on. Everything is coming off the same direction. But anytime something changes, this whole situation starts over again, right? So, anytime there's a puff of wind or we ease our sail for something, then this, for a little amount of time, starts over. We get back to that kata condition with both sides of the air coming off the sail at the same direction. But when it restarts, there's another little vortex is started up, right? So that actually ends up working like sort of a starter motor for something that I don't have the image on the computer, but we can pull it open here. Here we go. So that starting vortex serves to kind of start this rotation around your sail, around your whole boat, sort of in the air, right? So it sounds really weird to think about, but if we think of it more like this, right? We've got that little starting vortex. I'm trying to move my finger in the mirror camera, and it's acting like a little flywheel to start this bigger motion going around our sail. So what happens is that circulation and the lift that we're getting from here, they kind of work together, and that's kind of the full picture. I guess if you look at this mathematically by itself and you look at circulation mathematically by itself, they don't necessarily exactly work out, but together they do. And this guy has, people have wind tunnel data that's kind of showing both of these going on. So what's actually going on there is that if we think about that little starting vortex is spinning, starting up that circulation around your boat, it takes a while to get things moving, right? So that's kind of the explanation for why it takes so much longer to get your flow moving over your sail in light wind, right? And we know it. If you stall your sail, it takes a lot longer for your boat to get moving again in the light wind, versus if you're sailing around in kind of a medium breeze or heavy wind. Basically, as soon as you pull your sail in, your boat starts moving, right? So the more wind there is, the more force there is in that starting vortex, so that faster that circulation is going to start around your sail. Same thing for kind of the size of your sails, right? So the reason that a little dinghy is a lot more maneuverable, starts moving a lot quicker than a big keelboat, is just because the sail is smaller. So that big circle you're trying to start up spinning is a lot smaller. So it takes a lot less force to get moving again. So it definitely opens the door to understanding a lot more about what's actually going on there. It is also definitely weird to think about. But it definitely having some images kind of helps it make a little bit more sense. Right here, does anybody have any questions or super confused looks or whatever might be going on? Cool. I've totally mystified everybody, so that's neat. So basically, this is how does this fit in for us, like on a practical sense? Maybe not necessarily a lot. Like if a lot of you haven't heard either this or the Bernoulli explanation. We haven't heard what the right or the less right explanation. Right. So, but we're still able to go out and sail. So it doesn't mean that you can't get good at sailing if you don't know the scientific parts behind it. But certainly it makes it more interesting if you kind of know what's going on. Why do I need to put my sail in this particular shape, or why do I need to sit still in light air? So just kind of having all those backgrounds definitely helps a lot. Cool. So that definitely wasn't a super long one. I did not think I would be able to go for an hour with this sort of stuff. I was going to hopelessly confuse myself because a lot of this is newer even to me. So it's definitely pretty neat to figure out how this is all working. But what we'll do tomorrow, I think on the list I'd said we'd talk about some sail control stuff, how to make our sails do what we're wanting them to do with all this confusing science part. I think what we'll do is switch Wednesday and Thursday. Thursday I was going to talk about the slot effect and how that actually might be a little different than is often explained. It's not quite as crazy as this stuff, so it's okay. But I think that will come a little better before we talk through any more sail setup stuff. So we'll do that tomorrow, and then sail setup on Thursday. For anybody who is interested in hopping into the Green Fleet session later today, in about an hour, I guess, we are still talking about our basic sail controls, right? So how we change the shape of our sails for people who couldn't sit down and name them all off the top of their head, and what they do. So hope to see some of you there. And other than that, I'll see you tomorrow at 3.
Could I add something, Josh?
Go for it, Dan.
So with all the stuff about how lift doesn't have to be generated with the sail, and also just for general thoughts, I would expand that to say that that's something that works for everything that we call a foil. So sails are foils above the boat, and then you got your foils below the boat. Oh, did I just cut out?
You're good.
Oh, okay. Everything is red on my screen, but if you can still hear me, I'll keep going.
I can still hear you.
But below the boat, your daggerboard, centerboard, keel, and your rudder, or even if you're in like a moth or a wasp or something that flies out of the water, those foils are working in the same way, but they're much more efficient because unless you are an America's Cup boat, your sails aren't rigid. And like we said yesterday, a rigid foil is better and more efficient. And so your centerboard is also doing the same deal as your sails are, but obviously you're not moving the centerboard and it serves a different purpose. But those foils that lift those huge boats out of the water are very much doing the same thing. And then because they're using water, which is also thicker and bigger, that changes the game a little bit. But same deal above the water as below the water. Yeah,
I think that's definitely something worth bringing up. I think kind of 2 points off that. One would be, we're talking about this this illustration this guy's using is a flat plate, right? And obviously our sails are not flat. Airplane wings are not flat, because they are kind of set up for the most efficient shape they can be. Airplanes are designed, each different plane is designed to kind of have a different cruising speed. So whether it's a big passenger jet that's going hundreds of miles an hour, or a smaller, little single person plane that maybe does 40 or 50 miles an hour, they'll have a different wing shape. That curve on the top of the wing is going to be a little different, just because based on what speed you're planning to go at, you have the different shape is going to be more efficient. So it doesn't mean that you can't get lift if you've got the wrong shape. It just means that you'll get more lift for the amount of power you put in if you have the right shape. So for us, we have different wind speeds all the time. That's why our sails are flexible, so that we are able to kind of change them and make them a different shape when we have a different wind speed. But the lift will still happen. We just want to understand how to make it as efficient as possible. Other thought is, yeah, definitely the underwater, the foils under there, they are 100% creating lift for us under the water as well. If we kind of think of how the boat is moving through the water, it's not going perfectly straight ahead. So the centerboard and the rudder are not actually cutting straight into the water, right? It turns out that because of where that lift comes from on our sail, that lift is pulling our sail kind of up on the diagram, but that's not really corresponding with where our boat is pointing. If we go back to find one of these pictures here, this guy, yeah. So if we imagine this is our sail, our boat is certainly not pointing up at the top of the screen, right? It's kind of pointing maybe over here. And so a force that's going this way is pulling our boat to, if our bow is over here, it's pulling our boat to the right, which means that our centerboard or rudder underwater, instead of going like this into the water, they're kind of coming in at an angle, right? So even under the water, they're seeing this sort of thing, right? So if our sail is looking like this, if we look straight underneath our sail and pretend this is also our centerboard, then our centerboard is seeing water hit it kind of like this. And so now it has, if we just rotate this whole picture so that the arrows are coming from the top, now this whole picture works underwater, and it's creating lift that's going this way. And that's what makes our sailboat go in a mostly straight line, even though our sails on their own should be pulling us to the side. Because that centerboard actually gives us a little bit of lift as well. It's not just acting as a handbrake in the water, pushing up against the water. It certainly does that. But while it's doing that, it's also helping to pull us a little bit toward the wind. So that is why, probably most of us have had the experience of forgetting to put our centerboard down and trying to sail upwind and wondering why all we're doing is going sideways, because that's the only force we've got going on, is the sails pulling us sideways and no centerboard to help move us upwind, right? You'll get there eventually because your rudder's still in the water and that's given us a little bit. But if you've looked at the rudder compared to the centerboard, it's a lot smaller. So it doesn't give us anywhere near the amount of lift, amount of help that we would expect from that centerboard. Cool. So yeah, that's definitely worth kind of making that connection as well. All right, cool. So we have, for the first time in a while, we've only taken one Zoom meeting time. So we will see you on tomorrow, Wednesday at 3 p.m. Or for hopefully some of our Green Fleet will join us at 4:30 for talk about sail controls. All right, I will see you tomorrow.